Welcome everyone to this explainer. Today we're going to unpack a truly fascinating phenomenon. It's a scientific principle that perfectly connects our everyday, ordinary experiences right here on Earth to the vast, outer reaches of the cosmos. And the wild part? You've undoubtedly experienced it firsthand, probably without even realizing the massive cosmic implications it actually carries.
Okay, let's dive into this. Picture yourself just standing on a sidewalk. In the distance, you hear an ambulance siren approaching. Now, as it gets closer, the pitch of that siren sounds really high, right? Almost piercing. But the exact moment it whizzes past you, the pitch dramatically drops. It goes from a high-pitched wail to a noticeably lower drone. So why exactly does that happen?
To answer that, here's our roadmap for this explainer. First, the ambulance siren mystery. Second, anatomy of a wave. Third, motion and the Doppler effect. Fourth, why it is just an illusion. Fifth, beyond sound, light waves, and finally, real-world and cosmic applications.
Section 1. The ambulance siren mystery.
Section 2. Anatomy of a wave. Before we can solve the mystery of that moving siren, we really need to understand what sound actually is and how it travels from a siren straight to your ears. Basically, as any object moves or vibrates, it disturbs the air around it. Sound is simply a series of these waves moving through a medium. In fact, what you and I call sound is really just a sensation created inside our brains in response to these invisible, tiny pressure fluctuations in the air passing by our ears. And here is a crucial thing to keep in mind. The speed at which these sound waves travel remains constant in the given medium. So, the speed of sound depends only on the state of the air itself, not on the characteristics of whatever happens to be making the noise.
So in our street corner scenario, we've got two main players. First, we have the source, which is the thing creating the waves, in this case, our ambulance siren. And then we have the observer, which is the person or instrument actually detecting the waves. That's you, standing on the sidewalk listening. The relationship and the distance between these two players, that's the absolute key to unlocking this entire concept. Now, let's talk about how we measure these waves as they make their journey from the source to the observer. If you picture a sound wave kind of like a series of ocean swells, the wavelength is literally the physical distance between the crest of one wave and the crest of the very next one. Frequency, on the other hand, is just how often those waves hit you over a certain period of time. And this brilliantly illustrates how those measurements translate into what we actually hear. You see, our brain naturally associates a specific musical pitch with each frequency. So a short wavelength means those waves are arriving very frequently, a high frequency, which our brain interprets as a higher pitch. A long wavelength means the waves arrive way less often, a low frequency, yielding a lower pitch. Now, if that ambulance is just sitting parked, emitting waves in a perfect undisturbed circle, you're going to hear a steady, unchanging pitch.
Section 3. Motion and the Doppler Effect.
Now this is where things get really dynamic. What happens to those perfectly spaced waves when the source suddenly hits the gas pedal and starts moving? Well, as the siren moves through the air, it's still generating sound waves at that same constant speed of sound. But because the vehicle is physically moving forward, it's essentially chasing its own sound waves. Upstream, right in the direction it's moving, the waves get squeezed together, almost like an invisible accordion. The wavelength decreases, the waves arrive at your ear much more frequently, and bam, you hear a noticeably higher pitch. Downstream, behind the ambulance, it is the exact opposite. The vehicle is driving away from the waves it just emitted. So the waves get stretched out, the wavelength increases, they arrive at your ear less frequently, and the pitch drops.
Section 4. It is just an illusion.
Now, you might be thinking the mechanical siren on the ambulance is literally changing its tune, but our ears are actually falling for a massive trick of perception. So the crucial point is this: the actual mechanical frequency being produced by the siren never ever changes. The shift in pitch you hear on the sidewalk is purely an illusion caused by relative motion. Think about the paramedics or the firefighters sitting inside that speeding vehicle. They are moving at the exact same velocity as the siren, right? Because there's zero relative motion between them and the source of the sound, they just hear the siren at the exact same annoying constant pitch the entire time.
This incredible realization that waves compress and stretch just because of relative motion was actually first noted way back in 1842. The scientist who discovered it was named Christian Doppler, which, as you might have guessed, is exactly why this phenomenon will forever be known as the Doppler Effect.
Section 5. Beyond sound, light waves.
Let's scale this up a bit and see how it builds into something much grander. You see, the Doppler effect isn't just for mechanical sound waves traveling through the air. It applies to all waves, and that includes electromagnetic waves and light.
Now, while light waves are unique because they don't actually need an underlying medium, like air, to travel through, the Doppler principle still applies beautifully. When a source of light, like, say, a massive star, is moving toward Earth, its light waves get compressed. Those shorter light wavelengths shift the star's visual spectrum toward the blue end, which is what astronomers call a blue shift. Conversely, if a star or a whole galaxy is speeding away from us, those wavelengths get stretched out, the spectrum shifts toward the red end, and that's known as a redshift.
Section 6. Real-world and cosmic applications.
Because this effect is so universal, literally crossing over from sound to light to radio waves, it unlocks absolute superpowers for scientists and professionals all over the place. The Doppler effect is everywhere. When you see a police officer using a radar gun, they're bouncing radio beams off your moving car. By measuring the change in frequency between the beam they send out and the reflected beam that bounces back, they can calculate your exact speed. Meteorologists send radar beams up into the atmosphere. The Doppler shift in the returning waves helps them detect moving water to forecast the weather. Even in healthcare, doctors use echocardiograms, sending ultrasound beams through a body. The Doppler shift of those bouncing waves allows them to measure changes in blood flow and diagnose vascular diseases. It's truly amazing.
But honestly, perhaps the most mind-blowing application is happening right now, deep in space. Astronomers use the Doppler effect to hunt for invisible exoplanets orbiting distant stars. Think about it like this. If a star is completely alone, its light spectrum stays steady. But if a planet is orbiting it, that planet's gravity will tug on the host star just a little bit, causing the star to wobble slightly toward and away from Earth. As the star wobbles toward us, its light slightly blue shifts. As it wobbles away, it red shifts. By measuring these tiny regular shifts in the dark lines of a star's color spectrum, scientists can not only prove a completely hidden planet exists, but they can even figure out its orbital period and its mass. Hundreds of known exoplanets have been discovered using this exact technique.
So from the wail of a passing ambulance on your local street corner to the faint, wobbling light of a distant star harboring alien worlds, the Doppler effect reveals the hidden motion of our universe. It shows us that what we perceive is intimately tied to how we are moving through space. As our technology gets better and better at detecting even smaller shifts in light and sound, we really have to ask, what other invisible mysteries is the Doppler effect going to help us discover in our beautifully expanding universe? Thanks for joining us for this explainer. Keep looking up and keep listening.